So one of the things we didn't discuss, but is sort of obvious, is how to analyze the noise of a fully differential circuit. What you do is, this is on the left side I have a fully differential circuit, which in this case I have taken a simple differential pair, and it has certain common mode feedback circuitry that adjusts the bias of M3 and M4. And you are interested in the noise between these 2 points, okay, the noise voltage. What you do, of course, you can analyze the whole circuit, but you can also get it from the half circuit. You analyze the half circuit and you find the spectral density of it, and if you simply double the spectral density, you will get the noise of the differential circuit, okay. Because M1 is identical to M2 and M3 is identical to M4, their respective noise spectral densities are also identical. So you can get the spectral density of the fully differential circuit from the noise of the half circuit, okay. Usually much easier to analyze. And the common mode feedback components will add noise, but it will add in common mode, just like the noise from transistor M0. Okay? Is this fine? The next thing is for offset. Exactly the same idea. You analyze the mismatch of the half circuit. The only thing you have to be careful is, I have mentioned before that you can either specify the mean square offset with respect to some ideal device or between 2 identical devices. If you specify it between this device and an ideal device, you would have error in VT of each of them. Similarly, you can also add errors in current factor. Okay? Then you analyze the mean square error because of the half circuit using small signal analysis, and then the differential offset, the mean square value will be 2 times the mean square value of the offset of the half circuit. Okay. That is, if you have taken the delta VTs as mismatch between M2 and an ideal device and so on. But you can also consider it to be mismatch between 2 identical devices. That's typically how it is measured. You measure a number of pairs of devices. For instance, you could make current mirrors and then you inject some current and see how much in error it is. Okay. If that is what you have used, if that number is what you have used, then you analyze what comes out of the half circuit, and the differential, the mismatch in the differential circuit will be exactly same as that of the half circuit. Okay. That is, in the small signal analysis of the half circuit, what you use here is the mismatch between 2 devices. Okay. This is again quite simple. The delta VT between 2 devices will be square root 2 times larger than delta VT between the device and an ideal device. Okay. So this is a quick summary of what each of the op-amps does. If you look at the differential pair, it has a very low gain, and the equal signs means that I can't really comment on it. It's the same for all the others which have the equal sign. Okay. The noise and offset of differential pair, the telescopic cascode and 2-stage op-amps are very similar to each other. Okay. Now the noise and the offset of the folded cascode is higher, definitely. This is because of the extra biasing current sources that we need while folding the current. And the swing is very poor for differential pair and the telescopic cascode, and it's high for folded cascode, and it's the highest for the 2-stage op-amp. Essentially, to get the highest swing, you need to have a common source like structure at the bottom and a common source like structure at the top. That's the best you can do. Okay. Then as far as speed, by speed here I mean the highest unity gain frequency that can be achieved in a given technology. Okay. Now the differential pair has the fewest parasitic poles, then you expect that its omega u can be designed to be the highest in a given technology. Telescopic cascode is also pretty high. Actually, the folded cascode tends to be lower. I have put a plus here. I think this should have been interchanged. 2-stage op-amp can be designed to be a higher speed than folded cascode. Okay. There is an error here. This should be minus and this should be plus. Okay. So where to use the differential pair? DC gain is very low, especially as the voltages are shrinking. You can have, and in the low voltage technologies, GM by GDS is not very high. So you only get very low gains from a single stage. So you can connect the output to negative input and make a voltage follower for a capacitive load. Or you can connect a source follower here and connect it back to this and make a somewhat reasonable voltage follower even for resistive loads. Okay? And it's very frequently used in bias stabilization loops. That is, you have another transistor here and you want to use an op-amp around that transistor. Okay? This kind of circuit we are seeing, right? So, for instance, I want to mirror some current. I replicate the gate voltage simply by this connection, and I want to also set an accurate drain voltage at this point. So, I use an op-amp, and this is usually a single stage op-amp. Okay. The entire feedback loop is equivalent to a two-stage op-amp. So, this is the kind of place where you use a single stage op-amp very frequently. Okay. No, if you load it with a resistor, the DC gain becomes very, very poor. Yeah. That's the bottom line. Okay. Now the telescopic cascode, again, you can use it in only low swing circuits, and it's used frequently in switch capacitor circuits because of two reasons. Firstly, of course, the load will be capacitive in a switch capacitor circuit, and also you can arrange it so that the input and output common mode voltages are different. Okay. This is something that you can understand only by analyzing more circuits, or at least circuits with some specific applications. Let's say I make an amplifier, the usual inverting amplifier. If I want the output common mode to be different from the input common mode, that is, I need to have some voltage like this in quiescent condition. I need to have quiescent currents flowing through these resistors. Okay, that's usually not done. You can do it, certainly you can do it. It's a waste of current, and frequently the devices you use to draw these currents also tend to add noise. Okay, so most often if you have a continuous time circuit, the op-amp is operated with the input and output common mode voltages being the same. But the same is not true of a switch capacitor circuit. We haven't analyzed what switch capacitor circuits are, but it's enough to know that you have only capacitors. Now the capacitors can carry a fixed amount of common mode charge without drawing any current. Okay, so you can have the input and output common mode voltages to be different and use it more efficiently. We know that this op-amp, this is a single-ended op-amp, but even the differential version works better if the output bias is slightly higher than the input bias. Okay, you can get a larger swing in that way. Now if you insist that this common mode be the same as this, then your swing is even further limited. Okay, for all these reasons, it's useful for switch capacitor circuits. And the other place where it's used quite often, especially these days, is in the first stage of a two-stage op-amp. This is the only way to get any reasonable gain. If you use a simple differential pair, you probably can get a gain of 100 or 200 or something. You frequently need more than that. Okay, in very fine line processes, you may not even get that much gain. So to get a high enough gain from a two-stage op-amp, the first stage has to be a telescopic cascode. Okay. Yeah, we have more, but again, depending on how you choose the widths of these, it's possible to minimize the value of the parasitic pole. Okay, especially if you somehow design it so that this and this share the diffusion area without requiring a contact in between. That parasitic pole usually doesn't matter so much. Okay, that's true. certainly it's more speed limited compared to using a differential pair. But let's say you can't realize the gain in any other way. What will you do? You will have to use this one. No. Maybe it is a lower bandwidth op-amp, but I need a higher DC gain. DC gain translates to accuracy in a circuit, right? So there are cases where I need these are two orthogonal things. Like to get high accuracy, you need high DC gain. To get high speed, you need high bandwidth. So there are applications where you don't need the highest bandwidth, but you certainly need more DC gain. Okay. Now with a differential pair also, you can try to do it. Let's say you use the differential pair for the first stage and the second stage, a common source amplifier. If you increase the length of all transistors, you will get higher DC gain. But usually that the reduction in speed there is more than using a telescopic cascode. Okay. What's that? Yeah, you may not realize it. You may not be able to realize a stable op-amp with a very high gain and a very high bandwidth. That's it. Okay. Yeah, the question is scaling width is better than scaling length and width. I mean, we are talking about two different things, right? First of all, this current being proportional to W by L is valid only in strong inversion saturation for long channel transistors. Okay. When it goes into velocity saturation or anything of the sort, that is not valid at all. So in that case, scaling with L is just out of question. Okay. The only thing L does is if you use a longer channel device, you will have a larger parasitic capacitance. No, you can't do that. No, I'm talking about during the design process. I'm not saying that you take a design and then you scale all W's and L's by equal amounts and in the same proportion and get a higher gain with the same operating point. That's usually not possible. What I'm saying is you take the same topology perhaps. Now you increase all the lengths and widths. Perhaps not in the same proportion. You will have to design it. That's part of the design porting process. Okay. But you will get a higher DC gain with higher length, longer channel devices. That is for sure. But maybe it's not that you will have to double the length and double the width and everything is fine. You may have to do something more than that. Okay. So, as usual, you have a trade-off between accuracy and speed. For accuracy, you need longer devices. That is, you need higher DC gain and lower offsets, right? For both of these things, to get lower offsets, lower flicker noise and higher DC gain, you will need longer and wider devices, which goes against getting high speed. This is always a big trade-off. Okay. Next is the folded cascode. This gives you a higher swing, but it also gives you a higher noise and offset because of these current sources. Okay. And also it tends to be, to a first order, the expressions look the same, but the parasitic capacitance at these nodes is a lot higher. Okay. So it tends to give you lower speed than a telescopic cascode in a given technology. The fastest telescopic cascode op-amp you can design will be faster than the fastest folded cascode op-amp you can design. The second, one of the differences is this extra node with its large parasitic capacitances from M9, M10, M5, M6, M1, M2. The other thing is when you make a telescopic cascode, the signal path has only NMOS transistors. Okay? That is, at least in a high speed application, you will use NMOS input pair and NMOS cascode. Whereas here, you will always have both types of transistors. You will have NMOS and PMOS. So that again tends to work against high speed. Okay? So the high frequency performance of a folded cascode is usually poorer. Again, you can use it for switch capacitor circuits because you have capacitive loads. Now, there is not much reason to use this as the first stage of a two-stage op-amp because you don't need that much swing and you can do better with a telescopic cascode. Okay. Now, what happens is we have not studied a class of op-amps called class AB op-amps. in that case, the first stage tends to look like a folded cascode. Okay. We'll look at one example of it afterwards, but that's something, that's just a piece of information. Next time you see a class AB op-amp, you can recognize the first stage to be a folded cascode. Okay. Now, two-stage op-amp, it gives you the highest swing and you can use it with resistive loads. And also when you want to drive heavy capacitive loads at a high frequency, you tend to use a two-stage op-amp. Okay. Essentially what the two-stage op-amp does is it divides the responsibility of getting gain and bandwidth. To get high gain, you need to have high DC gain in the first stage. And to get a high bandwidth, the second stage has to have a large GM. So potentially you can use shorter transistors and less complicated circuitry in the second stage, and use a telescopic cascode or even slightly longer channel transistors in the first stage. So this will tend to give you a better combination of high gain and high speed compared to any of the other architectures we have, like the folded cascode or the telescopic cascode. Okay. So this is sort of the standard op-amp. If you can't use anything else, especially when you have resistive loads, you use this, and you have capacitive loads at high frequencies, you will tend to come to this stage. Okay. And a class AB op-amp always looks like a two-stage op-amp or more stages. A class AB op-amp has a separate output stage. I will describe a bit briefly now, but it always has at least one output stage and something driving it. So to design a class AB op-amp, you need to understand how a two-stage op-amp works. Okay. No, you may need high DC gain in the application for the op-amp. Okay. What's that? Oh, because you can afford to have a second stage with a low gain. Well, the question was, what makes this op-amp so good for driving resistive loads? So you can make the second stage with a relatively low DC gain while it is driving a resistive load. But you can put all the burden of getting DC gain on the first stage. You can use a cascode stage, right? Using cascode in the first stage will improve the DC gain, but in the second stage it won't do anything for you. How is that? I can't. You can't. I mean, you can use it, but the DC gain will be very low. Yeah, I said you cannot use it, right? The only way you can use a simple differential pair to drive resistive loads is to use a voltage follower. Okay. So if you drive resistive loads with something that has a very high impedance, then the gain depends only on the GM of the driving stage and the load conductance. Okay. So that's why here the second stage gain will be low, but you can afford to do that. You get all of the gain from the first stage. Yeah. Yeah, that's correct. Yeah. Why do you think that folded cascode is going to be always lower speed than the second stage? So the question is, you have a certain load for the folded cascode and certain load for the two-stage op-amp. Okay. Now, you have to, in this case, in the folded cascode case, the input GM divided by the load capacitance is the unity gain frequency, and all the parasitic poles have to be beyond that. Okay. So if you have a very heavy capacitive load, you have to realize a large GM and use a large current. Yeah. So this pole also tends to be at a lower frequency. Okay. The non-dominant pole also falls down, right, as you increase the device sizes and the currents. And the other Other point is here I can't make these transistors minimum length because then my DC gain will go down a lot. In a folded cascode, the gain depends on these transistors, all of these transistors, right? The DC gain part of it. So I can't, for instance, I can't use minimum length devices here and try to get a very large gain. If I do that, my DC gain also falls down. Sorry, very large bandwidth. What I meant to say was, you need to realize a large GM to drive a large capacitive load. But I don't want to use minimum size devices here because in that case, my DC gain also falls down, right? Because the impedance of this contributes to the DC gain. Whereas here, the two problems are somewhat separate. I can use minimum size, minimum length device here to get a large GM for this, okay? And I use whatever I want in before that. So it looks like a better trade-off. No, but why use a simple differential pair in the first stage in that case? I would rather do with a telescopic cascode, yeah.
The point is that depending on the output gap, there might be cases where we can actually realize better speed for the folded cascode.
Perhaps, but I mean, I don't know. Maybe if you explore all of the design space, perhaps there are some cases where you can do this. See so you have some load capacitance, okay. Now I want a certain omega u. Now in a folded cascode, what is the GM1 I need? Omega u times CL, and all of this should be greater than omega u, okay. Something greater, let's say. Now in the two stage, P2 is, sorry, GM2 must be greater than P2 times CL, right? P2 is GM2 by CL, roughly speaking. So I want the second stage GM to be more than this. Okay. Now what you have to do in a folded cascode, you have in a folded cascode, for a folded cascode op-amp to work properly, you have to use the same current here as in the second stage. Slew rate. Yeah, that's correct. Yeah. Okay. Whereas in the two-stage case, I use a large current here, but I can potentially scale it down. Of course, I can't scale it down beyond a certain limit because then the parasitic pole also starts moving, but I can scale it down. So generally, it appears to be a better trade-off. Okay. But I mean, the advantage of folded and telescopic cascode is that you don't have to worry about Miller compensation. You don't have to have special compensation structure. Your load capacitance will do the compensation for you. Yeah. Output? Yeah. No. When you use, the question is when you use a op-amp as a voltage controlled voltage source, the output resistance should be very low. So how will any of this help? All of these have high output resistance. So you are interested in the output resistance in feedback, right? The output resistance in feedback is a lot lower than the open loop output resistance. So that's how you get the low output resistance. Now of course, if you put a two-stage op-amp in feedback, you will get lower output resistance than if you put a folded cascode or a telescopic cascode in feedback. Okay. But still, you shouldn't look at the open loop output resistance. It's the closed loop output resistance that matters. Now, the other trade-off that you may worry about is whether to use NMOS or PMOS in the input stage. So usually NMOS is preferred for higher speeds because it gives you high GM for the same current. And in case of a two-stage op-amp, it's hard. Now one of the stages will be NMOS, the other stage will be PMOS. So it's up to you to decide whether you want to make the output stage NMOS so that you get a large GM from it, or you make the input stage NMOS and get a large GM from that. Usually output stage is what matters. Okay. And there are even two-stage op-amp architectures where the input stage is NMOS and the output stage also is NMOS. You need some kind of level shifting between the two stages in that case. Okay. Usually NMOS transistors have higher flicker noise when you bias it for the same GM and use the same length and so on. But this is not universal. There are processes in which the PMOS has higher flicker noise. So that may be also a point of choice, that is, depending on how important the noise is, you may choose NMOS or PMOS. Okay. Any questions?
So, giving a compensation more from the fact that you know the load capacity. Suppose I want to design a value from the solar. I don't know the load capacity. So how do I do it?
Yeah, the question is, if you don't know the load capacitance, how will you use it? Now, there are probably architectures in which that also works, but generally if you have an infinite range for load capacitance, then the only thing that will work is some GM-like stage. If you have a simple differential pair, that will always work. It will become slower and slower as the output load capacitance increases, but it can be stable. Okay. Whereas a two-stage op-amp, if you increase the load capacitance beyond a certain point, it will become unstable. That's the trade-off. Okay. So somehow, basically, if the load capacitance, the pole associated with the load capacitance, if that's the dominant pole, then there is no problem. You design it for the lowest value of the load capacitance. Then as the load capacitance increases, the dominant pole only moves inwards. In that case, you will only lose on bandwidth. You will not have any problems with stability. Whereas in a two-stage op-amp, the load capacitance is associated with the second pole. If that pole moves inward, then you will have a stability issue. Okay. So usually you can only design it for a certain range that is known. Okay. Now, if it is not known in advance, but it is known while using it, meaning you know what is going to get connected to it, but it could vary with time. Then what you could do is you can vary the compensation capacitor as a function of load capacitance. That is sometimes done. So sometimes what happens is maybe the op-amp is driving a structure like this. Okay. Here you have for whatever reason you have a switched array of capacitors. Okay. One case where you could see this is, let's say you make an integrator. Yeah, that also, an A to D converter. If it's driving an A to D converter, perhaps it is switching different amounts. Or you have an integrator with variable unity gain frequency. Then you switch these capacitors. Then it is driving different loads. Then what you do is, inside the compensation capacitor also can be switched based on the same control word. Okay. So you will have to do something like that to get a stable two-stage op-amp with a varying load capacitance. Okay. Otherwise, I mean, if you have no information other than the largest load capacitance, all you can do is design for the largest capacitance and live with the low speed and the consequently higher power dissipation. Okay. Anything else?
So, for the general purpose op-amp design is always best to start with testing full cascode and design put a load cap to begin with so that it's already compensated.
No, I mean, a general purpose op-amp design also needs to have other qualities. Like it should have relatively low output resistance. When I say general purpose op-amp, things that you buy off the shop like 741. Okay. For that you need to design a special output stage which isolates in which case also the non-dominant pole may be somewhat independent of the load capacitance. Because if you look at general purpose op-amps, they have a special output stage. They'll have three stages. They'll have something like our two-stage op-amp and followed by a voltage follower or something which buffers the load. Okay. So if you want to make a general purpose op-amp that is used in any application, then probably that's the structure you have to go to. But yeah, if you don't care about speed at all, like in many biasing circuits, you don't care about speed, then you go with a simple differential pair like thing, then even if the load capacitance becomes larger, all you are doing is sacrificing speed. Okay. Yeah. Yeah, it's actually a debatable question. You have to make a judgment based on what disturbances are there in your circuit. Okay. What are the common mode effects that you are going to get? So one of the problems might be that so let's say some circuit is very sensitive to distortion, right? If you apply a differential swing here, what will the swing here be? I mean, differential large signal swing. It will be a rectified version, right? It will be at twice the frequency. That will induce common mode currents at twice the frequency. So if you want to suppress this, then you need a common mode feedback whose bandwidth is nearly twice the bandwidth of the differential signal that you are interested in. Okay. So it entirely depends on what disturbances you expect. Okay. And sometimes it may be some startup. For instance, startup or let's say some current, common mode current is being drawn and then suddenly it becomes zero. So how fast does it come back to the common mode voltage? Or if you have a common mode step, how fast does it get restored? That decides the bandwidth. Now why can this happen? So it may not be a current source, it can be a capacitor also, right? So let's say I have some amplifier and I have some load capacitance that gets switched into both the outputs. Okay. Now the following circuit will also be fully differential, so it is symmetric about this line. But maybe the two capacitors were charged to zero, now you have to charge it to some voltage. So that will induce a common mode step as well. Okay, how fast does it recover from that? Those kind of things decide. So that is more or less decided by simulation. You need to know which way to go. That's the bottom line. Yeah, high DC gain means I am talking about maybe hundreds, right? Yeah, you would like the common mode to be stabilized accurately. Otherwise, you already have a relatively low swing to start with in today's low voltage technology. Now, if you lose some of it because of common mode biasing error, then you are unnecessarily wasting your available voltage headroom. Okay, you can apply smaller signals in that case. So, to reduce distortion, you should set the common mode point accurately to the optimum value. For that, you need a reasonably large DC gain. In addition to that, you have to make sure that you don't have systematic offsets in the common mode. How it helps? So let's say this is the fully differential structure and we are trying to apply common mode feedback around this. Okay. I'll use a resistive common mode detector. Doesn't matter what I use here. So in this case, I'll derive this feedback from the drain of the right side transistor. Okay. Now what do I apply here? This is VCM ref. Okay, this is the desired common mode voltage at the output. So this is the actual common mode voltage at the output. If these two are equal, what is the current flowing here? This is, let's say, I20 by 2. Okay. And this is I0 and these two are I0 by 2. Now if you look at this transistor, this and this. So these three transistors form a current mirror. Right? So when I20 by 2 is flowing here, I0 by 2 must be flowing here. So that must be a consistent solution. So in that case, this point will stabilize to VCM ref. So if something less than I0 by 2 is flowing here, let's say, if you analyze this current mirror, when I20 by 2 flows here, something less than I0 by 2 flows here. What should happen? The current on this side must increase. Okay, which means that this voltage has to go below VCM ref. Okay, similarly similarly the other way around. So you can have, if you don't make sure that this current mirror naturally gives you a current I0 by 2, when you push I20 by 2, you will have systematic mismatches. Okay. Yeah. No, the current density has to be equal. The argument was that we are wasting too much current in the bias here. Is that the, No, but I can scale this down, right? Maybe this is taking 1/5 the current and it has 1/5 the width also. Yeah, so that will be a problem. Meaning, if you want if you want that much accuracy, then this drain also has to be somehow biased to the right value. Okay. Now, these drains will be at VCM ref, or supposed to be at VCM ref, and this will be at VD minus VGS. So that will certainly give you an error. Yeah, if you want the error from that also to be suppressed, then you have to put this in a more complicated feedback loop. Okay. You can't help that in this particular case. Yeah. Yeah. Exactly won't match because of the drain voltage error of this. Yeah, that's correct. Yeah. Now, if you design, the situation will be much better. Let's say if the load was a cascode load. Okay. Then in the common mode feedback also, you can use a cascode load. And you will take the feedback for this from here. Now in this case, these three are more or less equal if you bias it from the same cascode voltage. So in that case, the error will be much lesser. The problem comes when you have a load that is not cascoded. Okay. So if you have a telescopic cascode, this problem goes away anyway. Oh, okay. Then you will have to further compensate it. You may have to add Yeah, that's correct. That's true. Sometimes that's a trade-off also. Just to reduce just to make the common mode feedback loop stable, you will end up adding some load capacitance to the differential path. That will worsen the differential response to some extent. So when you are designing a fully differential op-amp, you will have to iterate, you will design both this and this together, right? So you will have to iterate to get the best possible speed for the differential path. But yeah, it's true. Maybe if you had an ideal common mode feedback circuit, you will get a higher speed. That's possible.
Sir, when we use the CCM, it is in parallel with that asking.
Yeah.
That the value of the CCM should such that the zero that it introduces should cancel, or let's say close to cancel the pole that RCM.
Yeah, that's correct. Yeah. So perhaps the response of the common mode feedback circuit is like this without RCM. Okay. So let's say the pole because of RCM, the response because of that is something like this. Okay. Now the CCM should make it something of this sort, so that it happens before, the flattening should happen before that point. Okay. The question was about the common mode capacitance, capacitance used in the common mode detector. Now, let's say the rest of the amplifier has this magnitude response. Now, if you cascade it with a low pass filter whose corner frequency is RCM times the input capacitance of the common mode detector, okay, then you will get a response of this sort, which is unstable. So, in that case, you introduce a 0, and this 0 must be before the unity gain crossing of the common mode amplifier's response. Okay. In that case, you will get something of this sort. Okay. It will affect the common mode bandwidth, but it will be stable. Anything else? In the very first class, I had put up this slide. Hopefully, you did that. I don't know. I'll see you next week. The idea was to learn something about negative feedback and also realize those circuits at the transistor level. And this is what we went through. I think we finished most of the things that I intended to finish, except the last part about applications. The band gap reference, I think you got the idea by working it out in the first assignment and the last. The constant GM bias generation we didn't do at all, but if you remember in the first assignment there was a circuit involving transistors with different widths, and there was a resistance in series, very similar to the band gap structure but with MOS transistors. So that if you apply feedback to that, then that also gives you a current which tends to make the GM constant over temperature. Okay. So normally we have learned how to bias a transistor at a constant current and of course at a constant voltage, but you can also bias it at a constant GM, but the bias generation circuitry needs to be more complicated. So what you should be able to do now, you should be able to analyze negative feedback loops for stability. So this includes like if you come across discrete op-amp circuits and so on, you should, the data sheet gives you some application notes on how to use an op-amp, and many times those things, the schematics can look pretty complicated. Maybe depending on what op-amp it is, maybe it is like this with something here and then something here, etc. So all those things you should be able to analyze now. All that is doing is to introduce poles and zeros in the right places so that finally in the loop gain you have 20 dB per decade at the unity gain crossing. Okay. And compensate, if you find that your circuit is unstable, you should be able to compensate it also. The main idea behind compensation is to provide a high speed path in the feedback loop, right? The reason for instability is you have multiple stages with comparable delays. When you put that in feedback, you will end up with oscillation. So typically to have stability, you should have only one stage in feedback. That's the bottom line. Or in terms of the frequency response, you should have 20 dB per decade crossing at the unity loop gain. Okay. I think we have gone through design of transconductors and op-amps, that is single and two-stage op-amps, and also we know how to design appropriate biasing circuits. Depending on the accuracy required, you can replicate the VGS, VDS and put the bias circuit also in feedback loop if necessary in those things. Okay. Now going forward, if you come across other op-amp architectures, and there are many, some of them are minor variants of this, some of them are enhanced ones, like instead of 2 stages you can have 3 stages and so on. Okay. So those things also you should be able to understand with some work and design fully differential circuits, and finally analyze circuit noise and offsets. Okay. Where will you see all these things? So for instance, you can have a voltage regulator which typically consists of a band gap reference and a DC amplifier. Okay. This op-amp and this transistor constitute the amplifier. Usually the only special part about a voltage regulator is that this transistor may be very large because a very large current may be demanded of it. Okay. It should hold the output voltage constant in spite of very large changes in current. So this transistor tends to be very large. Usually the speed requirements are low in absolute terms. Okay, you're not looking for tens of megahertz of bandwidth usually, but because this transistor is large, it introduces a parasitic capacitance here, which is also large. So you will still end up with a reasonable problem for stability and frequency compensation. Okay, this is what you see inside most voltage regulators. And a current steering DAC. Those of you who have taken data conversion circuits are familiar with this circuit. Current steering DAC, a digital to analog converter, all it has is a number of current sources which can be steered one way or another. Now, if you know how to design differential pairs, you should be able to design this also. Main point in designing this is to see what swing you need for these bits so that it switches completely from one side to the other, and how to minimize the parasitic capacitance here, how to make sure that the currents are accurately matched. So you analyze the random offsets and systematic offsets if there is any, and make sure that that is smaller than your LSB value. That's all that is there to design of a current steering DAC. Okay. Besides, of course, designing the digital decoder to get these control bits. And feedback amplifiers, again, you are familiar with. Now you should be able to analyze these for stability with some confidence. And again, I think this is some other familiar circuit. It's a filter using opamps, R's and C's. Now you should be able to put your own opamps here and see how it works. Okay. So what next? If you, those of you who are interested in analog IC design can look at these things. These are also very useful opamps, which we didn't have time to cover in this class, but they are enhanced versions of what we have studied. Okay. So one of them is a class AB output stage, and you can have more than two stages. Why I stop at two stages? Then you can have what is known as a multipath opamp, which is actually very interesting also. Yeah. Different from what? Yeah. No, I don't understand this. 1 second. What was the question? When you have a two-stage? Yeah. Okay. Meaning I make an amplifier out of it. Yeah. No. First of all, you said something about fully differential. The two-stage, whether it's single-ended or fully differential, should behave the same, right? Is that okay? I design, let's say, an input differential pair, certain output stage with a certain Miller compensation capacitance. Now I simply replicate the second stage on the other side and the same Miller compensation cap. I should get the same bandwidth. Now the phase margin will be slightly improved because of the absence of the mirror pole and zero. Okay. Besides that, there should be no change. Now when you put that in feedback, you are saying the 3 dB bandwidth is not the same as unity gain frequency. Huh? Okay, single-ended two-stage op-amp. What's the issue? Okay. Yeah. So if you, the problem he is raising is, this has a certain omega u, okay, and you put it in unity gain feedback. What should be the 3 dB bandwidth? Omega u. Why would it be different from omega u? So if this op-amp's response is purely first order, then the 3 dB bandwidth will be omega u. Okay. If there is another pole here, when you put it in feedback, the poles can become complex and the bandwidth can increase. In fact, if you place the non-dominant pole at twice the unity gain frequency, you can get the highest bandwidth without peaking. This we have seen, right? The bandwidth will be square root 2 times omega u. Is that what you saw? Yeah, I think that's probably what it is. You should look at the phase shift of the op-amp as well, and you will be able to figure out more easily if there are extra poles close to the unity gain frequency. How many? No, I can only explain it sort of mathematically in terms of, we have seen this root locus and so on, right? So there you see that the poles become complex. Okay. What's that? Oh, how will that increase the bandwidth? So let's start with an open loop response where the non-dominant pole is really far away. Okay. So in that case, the closed loop response will be pretty much like this, where this is the 3 dB bandwidth. Okay. In reality, it will droop this way. Okay. Now, as this point moves closer in, what happens? The circuit moves towards instability, right? So that means that the circuit has a tendency to ring at a particular frequency. What you are doing is you are just balancing that. Here it is drooping off. Okay. For a sinusoidal input, the amplitude is dropping off. But then if it has a tendency to ring at this particular frequency, then that added to your input can make the response something like this. Okay, it will make it flatter. That's what happens. Now, of course, if you bring it too far in, what will happen is something like this. So that's not a very useful amplifier. So essentially, you are bringing in a little bit of tendency to ring. Okay, in a step response, if you look at if the dominant pole is here, the step response looks something like this. And if the non-dominant pole is here, the step response looks something like this. You introduce a slight tendency to ring just at the right frequency, so that in the sinusoidal steady state response, you see a flat area for a larger range of frequencies. Okay. What's that? To do what? No, if your GM is very large, the pole moves this way. To do this or this? Yeah, it should be high enough. I mean, what do you mean by very high? It should be high enough to get your second pole beyond the unity gain frequency. Yeah. See, in a two-stage op-amp, the first stage GM per se is not an issue. Okay. It's the first stage DC gain that's a problem. First stage GM is an issue for the noise, offset, all of these things. And also, you can't scale it down indefinitely, because then your compensation capacitor becomes very small. Then all of the approximations we use for the non-dominant pole, etc., break down. Okay. I don't know, maybe 5 times, 6 times, something like that. Yeah. You will always have additional poles, right? Because of that, it tends to ring. In fact, this is good. Why would you want to make it, why would you want to take the effort to put the GM very large, put the non-dominant pole here and get a smaller bandwidth? In fact, you should try to adjust it so that you get the optimal, a high bandwidth for the same circuitry. Okay. Pardon? Yeah. Yeah. So that's why we don't adjust it for a significant peaking in the frequency response. We adjust it for no peaking. The bandwidth will extend as the non-dominant pole approaches the unity gain frequency. But you don't let it approach indefinitely. Okay. You stop at a point where there is no peaking in the frequency response. Now, if your op-amp has a response of this type, okay, the point to stop is when P2 is 2 times omega u. Okay. So, yeah, you can't bring it in indefinitely. Then you will have significant peaking in the frequency response. And also significant amount of ringing in the time domain response. See, the idea is to improve bandwidth. In terms of steady state response, that means for a larger range of frequencies, you get a constant gain. In terms of time domain response, it settles to the desired output faster. Okay. In fact, with some ringing, it may settle faster than without ringing. That depends on the ringing, that depends on the settling accuracy you are interested in. Now, there is no point in making it like this. Okay. Now, it is going to take very long time to settle. You don't do that. You just let it ring only a little bit. I think we are way out of time. Just the last part. So, in a class AB op-amp, we saw that the class A op-amp, you guys have class now? Okay, I'll take 5 more minutes, that's all. In a class A op-amp, we saw the limitation of having a constant current source here. Okay. What is the largest current you can draw into the op-amp? This one, right? I1. So, the best you can do is to cut off this transistor by raising this voltage. Then I1 will be drawn in. So, the maximum current that you can draw is I1, so that limits your swing limit. Or rather, for a given swing limit, you have to use a large I1. Let's say you have a very heavy load. Okay, very heavy resistive load. For instance, if you are driving a headphone, what's the load of a headphone? 16 ohms. So, something very small. Okay, smaller than what you have ever designed for. So, in that case, if you have a quiescent current enough to drive 16 ohm, 1 volt across 16 ohms, that corresponds to how much? 62.5 milliamps or something. So, maybe you need 100 milliamps of quiescent current. That's a lot of power. So, what you must have is a way to increase this current when necessary. Okay, and have a small quiescent current. That's the idea behind a class AB op-amp. You maintain a small quiescent current, but you can drive a large current in both directions when necessary. So, what you do is, before this used to be a transistor with a fixed bias. Now, this is a transistor with some bias, so that it carries a certain quiescent current. Plus, the signal that appears here must also appear at this point. You need to make some arrangement to ensure that. That will make sure that as this voltage rises, M11 moves towards cutoff, but M12 carries more and more current. Okay. Similarly, when V signal decreases, this cuts off and this drives more and more current out. Okay. That's all. That's what is there in the class AB op-amp. And what you need in addition to this is an arrangement to provide V signal here, but with a different bias value. The bias value should be such that a small quiescent current flows through M11 and M12. Okay. So, it's used with very heavy loads usually. This is the only way to maintain a small quiescent current and drive a heavy load. And this is the full circuit that does that. This part of the circuit provides the same signal swing here and here, but with different bias values. Okay. I'm not going to discuss the details of this here, but this is very much like a two-stage op-amp. And you can also see that this part looks like a folded cascode. So, these are some references, and one of Shanti's students is working on a different way of providing the bias by using a capacitor as a battery. Okay. This is the last one is another class AB op-amp. We used that in the delta sigma modulator paper that I showed to the class the other day. Actually, it's not very good. It has some problems, but you can still look at the circuit. You should be able to understand how that works also. Then you have three-stage op-amps. This is when you need very high DC gain for high accuracy. For instance, for high accuracy DACs, you need this. Okay, when you want to settle to one part in for 16 bits is 65,536 or something, right? When you want a DC gain of 100,000 or more, you will need to use something of this sort. And it has very complicated compensation schemes, and it can generally be done only at very low speeds. Okay, I mean certainly lower than what you can design a two-stage op-amp for. So, this is a good paper on a number of techniques to compensate a three-stage op-amp. Okay, and one of your seniors, Hari Prasad, is also working on a three-stage op-amp. You can see these are the sort of structures used in a three-stage op-amp. So, you don't need to know anything else other than that. It's very complicated. Okay. So, all this you need because to be able to compensate a three-stage op-amp, you need all of this stuff. And this paper systematically analyzes all of them and tells you which is good, which is bad. The other very interesting stuff is this multipath op-amps. Normally, in a two-stage op-amp, we have this and this. And we put a capacitor around this to compensate. Instead of that, here, you put another GM around the whole thing. So, this gives you a slow high gain path. This gives you a fast low gain path. To close the feedback around this, for high frequencies, this path is almost not there. Okay, if you choose the GM1, GM2, GM3 correctly, it will be a stable op-amp with high DC gain, and you don't need any compensation capacitor. Okay. So, in a given technology, you can design the highest unity gain frequency using this. Now, it's not very clear it can be used for discrete time applications because you have multiple paths, you will have multiple poles and zeros. Okay. So, that can give you very slow settling in the time domain. So it's not 100% clear, but we are also looking at this. This thesis is a very good reference on this one, and you can go one step further and have 3 paths, 2 paths, and 1 path all in parallel. And this is a paper that was published recently which uses a similar op-amp. The main problem with this type of op-amp seems to be that you can't design it for high swing. Okay, you can design it only for a swing that comes out of a differential pair. So that's it. These are some references. So this is the end of the